Hi everyone, this is Guei-Yuan. I'm going to talk about the C4 high performance SIMD programming on Intel GPUs. This is joint teamwork thanks to all the authors listed here who made a great contribution to this paper. Mainstream GPU programming on the market today adapts a single instruction multiple threads or the single program multiple data programming model. Typical examples are OpenCL and CUDA. Intel GPU ISA is a single instruction multiple data SIMD architecture. Compiler is supposed to bridge the gap between the programming language and the underneath hardware. Although our compiler strives its best to generate optimal code, we still found cases that the user cannot harvest the full computation power of Intel GPUs. One simple thought is why not go all the way to assembly programming? Actually, we did do that years back for media codec. Hundreds of the kernels were written in assembly. We achieved the performance we wanted. However, assembly programming is known error-prone and suffers debuggability. Also, as architecture evolves, those kernels are no longer portable and requires the rewritten. Maintainability and productivity were greatly impacted to the point we must take some actions. We need a language that allows a developer to do meta programming. The goal is to achieve the assembly performance while obtaining high-level maintainability and debuggability. The language is tailored for specific developers like a kernel and the library developers, not broader general users, because meta programming requires to know the underneath hardware knowledge to fully explore the hardware capabilities. Let's see how we map the SIMD and the SIMD programming model on Intel hardware. This picture shows the high-level view of how we map the OpenCL SIMD model. An OpenCL program is a collection of parallel execution of work items. Work items are mapped to an index space called ND range, which can be 1D, 2D, or 3D. ND range is further decomposed into work groups. They can be launched onto one compute unit to be executed. Users write a scalar code for one work item. The users may decide or the compiler to pack the multiple work items into one subgroup that can be launched to be executed by one hardware thread. Work items in one subgroup, they share the one register file. And from one work item's perspective, it sees its own portion of the register data, shared local memory, L3, and global memory. Work items in one subgroup resides in the same register file. They cannot see each other's data. They need to rely on subgroup extension shuffle to shuffle data. Adopting similar ND range concept, CM has thread group, which can be 1, 2, and 3 dimensions. What's different from the OpenCL model is that CM users writes the program for one hardware thread instead of work item. One instance of program sees the whole register file, shared local memory, L3, and global memory. The program explicitly expresses data parallelism without relying on the compiler to pack the work items to achieve parallelism. And data of register file are directly manipulated by the program. Due to the time limit, I only cover features that will be used in the example of this presentation. Other features and details are described in the paper. If you have assembly programming experience, the first thing you care likely is how to map the variable to register. Furthermore, if hardware can do operations in parallel, you also care about how your algorithm can be expressed in terms of parallelism and to take advantage of hardware. CM achieves both while vector and the matrix data types. And by default, compiler maps vector and matrix to registers. If it fails, it will generate spill code with a warning message asking user to revise their code, for instance, using a smaller data chunk size. The example here, we declare a vector of 24 bytes and a matrix 4x8 float. Parallelism is explicitly expressed with vector and matrix operations, such as plus, minus, multiply, or logic operations. Operations of vector and the matrix means element-wise operation. That is, all the elements can be computed in parallel. We also have a reduction intrinsics such as sum, max, and min. Not necessary vector and matrix operation involves all the elements. This picture shows how we select the element from a vector and the matrix. Selecting elements from a vector takes two template arguments, size and stride, and another argument I, the starting location. Size is the selected number of selected elements. Stride is the distance between two adjacent selected elements. And I is the starting location. So the example here, using the previous page, vector 24 bytes, we select 8 bytes with stride distance 2, starting with the second byte, as highlighted in red color here. Similarly, we also select elements from matrix. It takes the 4 template arguments and the starting location ij. We need to indicate the number of selected rows, distance between 2 rows, number of selected columns, and the distance between 2 columns. The example here, we selected 2 rows with distance 2, and each row we have 2 elements, stride distance 4, starting location as 1, 2. And we also have other access functions like a row and column. Register is our precious resource. User can declare reference to a vector and matrix-based object. Reference does not take up a register space, only base object does. By doing this, operation can be operated in place without creating temp vector or matrix. The example on the right, M1 refers to the selected elements of matrix M. Any accessing to M1 is accessing to the selected elements of M. We also have another function, format returns a reference object. Format reinterprets the base vector or matrix with a different shape and type. On the example on the right, we have a vector of 4 integers highlighted in different colors. Reformat the 4 integers into 8 shorts and 4x4 byte matrix. Again, they all share the same register space. You can view format as a C union. Hardware has certain restriction on how data is accessed in register file. To write efficient code, users need to know how vector and the matrix are laid out in register file, so that they are aware their code, if their code hit a certain hardware restriction that prevent from generating efficient code. Vector and the matrix start at the register boundary, and rows are laid out consecutively in row major. There's no fragmentation. User may decide to add a padding for efficient code, namely trading the register space for efficient code generation. There's another useful operation, merge, that merges a value from sources. The first one, it copies the value from source when the corresponding mask bit is true. It preserves its old value when otherwise. So the second one merges from two sources. It takes the value from source one when the corresponding mask bit is true from source two otherwise, as shown in the example here. The first merge is mapped to a predicate move. The second merge is mapped to a native select instruction. With all the features we have shown so far, let's see how we can write a simple linear filter. It's a 3x3 box filter. The algorithm is simple. For given pixel position ij, we average 3x3 pixels surrounding ij. So the first thing we need to do is to decide the data chunk size each hardware thread processes. In this case, it's a 6x8 pixels. Each pixel has 3 bytes. And for box filter, we need to read 2 extra rows, one at the top and one at the bottom, and 2 extra columns, one to the left and one to the right. For 6x8 pixels, we need 8x10 pixel values, which is 8x30 bytes. For efficient data layout and the efficient memory read, we read in 8x32 bytes. Once the data is read, we select the 6x24 region starting at location 13, which is AIJ. And we sum it with another 6x24 data region starting at location 00, which is I-1 and J-1. We shift it by 1 pixel position, and that will be I-1 and J. Once we sum up all 9 6x24 data regions, we divide it by 9, and we write out the 6x8 pixel value. The addition of 2 6x24 data region is a SIMD 144 operations. The compiler breaks the addition into smaller chunk size so that they can fit it underneath the hardware SIMD width. Another example is sparse matrix vector multiplication. We use the CSR representation. It's a compressed sparse row representation. The matrix A is represented with 3 one-dimension arrays. A and Z has non-zero elements of A laid out in row major fashion. A column are the column indices of the corresponding non-zero elements. A row encode the index of a given starting position of a given row. The challenges of SPMV are the sparsity and the irregularity. The sparsity of input matrix may vary. Also, the non-zero elements per row may also differ. Let's see how we handle this one case. Assuming the input matrix is not extremely sparse, there are still a few elements, non-zero elements per row. Let's say average A or above. We let one hardware thread to process one row in this case. So for the example shown here, we have 7 non-zero elements shown in green color. For efficient reads, we rounded the number of non-zero elements to be loaded to 8, 16, or 32. In this case, we round up to 8. We load the data in. The next is we load their corresponding column indices. We zero out the entry that don't belong to this row using merge operation. With the given column indices, we use gather operation to read the data from vector X. The trick we do is we pattern one element at the beginning of vector X with value 0, so that all the entries that don't belong to the row will read the value 0. Then we use the DP4 intrinsic to take advantage of the hardware that can do dot product of 4 elements. The result of DP4 is stored in the first element position. Subsequently, we use a reduction sum to sum up the DP4 results. This chart shows the performance comparison. Workload were written in both the OpenCL and the CM. And CM outperforms the OpenCL ranging from 10% to 150%. And for the gem kernel, OpenCL and the CM, they all employ a similar register blocking strategy. Although the OpenCL is able to achieve this by using Intel's subgroup extension and mimicking a CM implementation, CM still outperforms the OpenCL by 10% because of the better register management. Other analysis is described in the paper. So this chart doesn't mean that you will see all the OpenCL workload with such a big performance gap. Many programs with a massive data parallelism that can be well expressed with the SIMD model, the performance gap will be smaller or in the same ballpark. Programmability is a common concern for the adoption of close-to-metal programming. One must carefully weigh the performance advantage against the potential productivity lost due to the high ramp-up time and requires the hardware knowledges. In our view, when writing a kernel, the job is not considered done when the kernel is functional. It is done when the desired performance target is reached. And very often the tuning consumes the most of the effort. Like we need to decide how to do the register control, how we do the data sharing, how to high latency, so on and so forth. During the early stage of the development of machine kernel, there was intensive debate on the choices of programming model. To do a fair comparison, our computer architects wrote some kernels using both languages. They log the development effort as well as the performance achieved. The table shows CM is able to yield higher productivity while achieving higher performance. Conclusion, this paper presents a high-level yet close to metal programming language for Intel GPUs. It exposes a hardware capability. It also achieved close to the assembly performance. By no means we try to attack the SIMD programming model. As a matter of fact, SIMD programming model has the beauty of the ease of programmability and the nice scalability. Many programs have achieved a decent performance. But in some cases, SIMD programming model carries a performance cost that can be difficult to overcome for Intel's SIMD architecture. And with the CM as a solid backend, different language front-end can target the CM as their backend. Examples are like a DB++, explicit SIMD, and the ISPC compiler, and the machine learning code generation tool. Thank you very much.